Look around you. Everything you see is made of something. Materials that shape our world. For centuries we discovered new materials by chance. Now we design them, arranging atoms to create substances nature never imagined. This is material science, the art of building a better future by mastering the building blocks of reality. Imagine fabrics that generate electricity or windows that change transparency at a switch. These are real goals, not science fiction. To achieve them, we must understand how atomic arrangements dictate behavior, moving from a macroscopic to a microscopic view. The possibilities are endless, but the combinations are overwhelming, far too many to test in a lab. Enter computational research. We now simulate and test new materials in a digital universe, predicting their properties before making them. This partnership between human creativity and computer power is accelerating discovery like never before. Our story begins with smart, organic materials, carbon-based molecules that respond to light in intelligent ways. These materials could revolutionize everything from internet lasers to solar cells. The next materials revolution is here, built with algorithms and processors, as we learn to command the very stuff of the universe. Let's dive into this new era of material design. A team of scientists recently focused on two fascinating molecules, phenylene and pyrene. These flat, stable carbon structures are perfect blueprints for building advanced materials. By digitally attaching electron-donating and electron-accepting groups, researchers could fine-tune how these molecules interact with light. All of this happened inside a computer, using density functional theory to predict properties with precision. Instead of months in a lab, they screened 24 molecular variations virtually, rapidly identifying the most promising candidates. Their goal: find molecules with exceptional optical and energy properties for next-generation technologies. This is science where prediction leads the way, guiding real-world innovation. To see why these molecules matter, we need to talk about light and nonlinear optics. Most materials respond to light in predictable ways, but some, when hit with intense laser beams, behave differently, unlocking nonlinear optical (NLO) effects. NLO materials are the backbone of high-speed internet, acting as switches and amplifiers in fiber optic cables. They also enable advanced lasers for surgery, manufacturing, and scientific discovery. The same properties that make great NLO materials often make them ideal for solar cells, capturing sunlight and converting it to electricity. Designing better NLO molecules means better tech, faster communications, more efficient solar panels, and a sustainable future. Organic molecules like phenylene and pyrene offer lightweight and flexible and affordable alternatives to traditional crystals. This research is paving the way for the next generation of devices that will define our century. The search for new NLO materials is a direct pursuit of better technology. The simulations revealed which molecules stood out. Pyrene-based designs consistently outperformed phenylene, thanks to their larger electron systems. One molecule, Pi3, emerged as the top performer, combining a pyrene core with strong electron-donating and accepting groups. Pi3 showed the highest nonlinear optical response and the smallest energy gap, ideal for both NLO and solar applications. The key insight: smaller energy gaps lead to better performance. Pyrene-based molecules also showed higher potential efficiency in simulated solar cells. This dual success means one molecular design could power both high-speed communications and solar energy. The digital search had found a family of multi-talented molecules. The environment matters. These molecules perform even better in certain solvents. Methanol, a common polar solvent, dramatically boosted the best molecules' optical responses. This makes them more practical for real-world devices, where controlling the environment is key. Computational screening now guides chemists, accelerating innovation and saving resources. Pyrene-based molecules are ready for synthesis and testing in next-gen lasers and solar cells. These discoveries could lead to faster networks, flexible solar panels, and a cleaner, brighter future. The journey to advanced technology starts small, with the design of a single, extraordinary molecule. Welcome back to For Science Salah Lotfy channel. In this special episode, I want to spotlight an inspiring figure in modern chemistry. Dr. Tazeem Fatima, a rising researcher from Punjab, Pakistan, who is making significant strides in computational and theoretical chemistry. Dr. Tazeem Fatima is a PhD researcher and lecturer at the University of Faisalabad. Her passion lies in designing advanced materials for optical and optoelectronic applications, the technologies that power our future, from high-speed data transmission to solar energy conversion. She is a specialist in computational chemistry, working with powerful quantum mechanical tools like density functional theory, or DFT, and time-dependent DFT, also known as TDDFT. These tools help her explore how molecules behave, how they transfer energy, and how they interact with light in both ground and excited states. But beyond equations and simulations, she brings a true spirit of innovation and mentorship, guiding students in applying theory to solve real-world scientific problems. Her research is focused on the smart design of organic materials through logical molecular engineering, tuning terminal groups, modifying the molecular core, and optimizing bridge structures. This allows her to boost nonlinear optical properties, which are vital for lasers, sensors, and photonic devices. What sets her apart is not only her scientific depth, but her commitment to interdisciplinary collaboration. Dr. Fatima integrates analytical thinking with digital modeling to tackle some of the most challenging questions in material science. Her work has already been published in peer-reviewed international journals, earning recognition for its quality and relevance in both academic and industrial circles. As a dedicated educator, researcher, and chemist, Dr. Tazeem Fatima represents the new generation of scientific leaders in Pakistan, those who are building a bridge between theoretical research and practical innovation. I'm proud to feature her on For Science Salah Lotfy channel as a role model for aspiring scientists everywhere. If you're inspired by her story, leave a comment below, and don't forget to subscribe for more spotlights on outstanding scientific minds around the world. Hey there, welcome to For Science Salah Lotfy channel. Today, I'm diving into a fascinating piece of research that blends chemistry, physics, and computational science. Work that could reshape the future of optical tech and solar energy. This study is called Systematic Computational Designing of Efficient Phenalene and Pyrene-Based Derivatives to Tune the Optical and Nonlinear Optical Response. It was published on May 20th, 2025 in the Journal of Fluorescence by Springer Nature. First, let's give a shout out to the brilliant minds who made this possible. Dr. Tazeem Fatima, Associate Professors Shamsa Bibi, Shabir Muhammad, Shaukat Ali, and Muhammad Yassin from universities in Pakistan and Saudi Arabia. Their combined expertise in chemistry and physics pushed this project to new heights. So what exactly is this research about? The team designed new organic molecules, based on phenylene and pyrene, that could revolutionize optical materials. These molecules aren't just cool on paper. They're built for real-world applications like high-speed data, laser tech, optical signal processing, and solar cells. What really sets this work apart is the use of quantum computational methods, specifically density functional theory and time-dependent density functional theory. Instead of expensive lab trials, these tools let the team predict how molecules will behave under different types of light and electric fields. It's like a molecular crystal ball. Here's how they did it. They engineered 8 new molecules, 4 phenylene derivatives, Phe1 to Phe4, and 4 pyrene derivatives, Pyr1 to Pyr4. By tweaking the core and terminal groups, adding pieces like methoxy and nitro, and swapping in atoms like nitrogen and boron, they could tune the properties for maximum performance. The results? Phe4 stood out for its exceptional linear polarizability, which is crucial for responsive optical materials. Even more impressive, Pyr4 showed a third-order nonlinear polarizability of almost 2,000 times 10 to the minus 36 ESU, a record compared to standard materials. This is all thanks to strong internal charge transfers and carefully optimized electronic structures. But it doesn't stop there. The team also checked how these molecules perform in solar cell simulations. Pyr1 led the pack with an open circuit voltage of 2.144 eV, suggesting it could be a top-notch dye sensitizer. The light harvesting efficiency for some molecules was nearly 99%, and every compound showed a negative free energy of electron injection. Translation, they can spontaneously transfer energy to semiconductors like TiO2, ideal for solar technology. So, what does all this mean? It's more than just theory. This research offers a roadmap for using computational chemistry to design smarter, more sustainable materials for everything from photonics to clean energy. A huge thanks to Dr. Fatima and all the associate professors for pushing the boundaries of science. If you're as excited by this as I am, drop your thoughts in the comments below. And don't forget, like, subscribe, and keep following For Science Salah Lotfy channel for more journeys to the frontiers of discovery. Sometimes the most profound revolutions begin quietly, in the world of atoms and electrons governed by quantum mechanics. Here, scientists are no longer just discovering nature, they're designing materials with properties once thought impossible. This is a story about that frontier manipulating light to create technologies that could redefine our world, from ultra-fast computing to clean energy. Imagine crafting a material molecule by molecule before it even exists physically. That's the power of computational chemistry. By simulating the dance of electrons, researchers can predict molecular behavior with astonishing accuracy, exploring endless possibilities without waste. This journey takes us into the heart of phenylene and pyrene, tiny flat sheets of carbon atoms that, when modified, become candidates for nonlinear optical (NLO) materials. NLO materials hold the key to controlling light in ways that defy intuition, enabling the next generation of technology. The quest for these materials is driven by our need for faster data and sustainable energy, solutions rooted in fundamental science. This is a story of vision, precision, and the beauty that emerges when we learn to speak the language of quantum physics. Every scientific breakthrough is a human story, one of collaboration and relentless curiosity. At the forefront are researchers from the University of Gujarat, Pakistan, leading intricate simulations in computational material design. Partnering with the University of Sargodha, they've created a powerful research hub, validating results and ensuring scientific rigor. The team's reach extends internationally, with the University of Jeddah in Saudi Arabia adding expertise and perspective. This collaboration shows how science transcends borders, creating a vibrant ecosystem where innovation flourishes. Their laboratory isn't filled with beakers, but with high-performance computers, navigating quantum landscapes to unearth extraordinary materials. Their work is a testament to the power of global collaboration, accelerating innovation in the digital age. What are nonlinear optical materials? To understand, consider how light usually passes through glass unchanged, a linear response. But with intense light, like a laser, materials behave non-linearly, altering light's properties in remarkable ways. NLO materials can merge photons, change refractive indices, and enable technologies from fiber optic networks to advanced medical imaging. The ability to control light's frequency and phase opens up powerful new applications. Scientists seek molecules with strong nonlinear responses, efficient, stable, and easy to synthesize. This is the challenge our team has embraced, designing molecules from scratch to push NLO technology beyond current limits. Their goal is not just good materials, but exceptional ones, unlocking a new wave of innovation. By mastering nonlinear optics, they're building the foundation for tomorrow's technology. Traditionally, discovering new materials meant synthesizing and testing countless compounds, a slow, costly process. Our researchers took a different path, building their laboratory inside a computer, using computational chemistry to design and test molecules virtually. They started with phenylene and pyrene, flat, electron-rich carbon structures, using them as molecular scaffolds. Their strategy, the donor pi acceptor, DPA design, attaching electron-donating and electron-accepting groups to create a permanent charge separation. This setup makes the molecules highly responsive to light. Using this approach, they designed 8 new compounds, 4 based on phenylene, 4 on pyrene, each a calculated hypothesis about how structure affects light interaction. Guided by quantum chemistry, they became molecular architects, drawing blueprints for tailor-made materials. All of this happened within the clean, efficient world of computer simulation. The team created 2 families of molecules, the PN series, phenylene core, and the PY series, pyrene core. Phenylene offers a triangular, electron-rich foundation, pyrene, a larger rectangular structure with even more mobile electrons. By comparing these cores, researchers could see how size and shape affect NLO properties. Both series use triphenylamine as the donor and 4 different acceptor groups, creating a gradient of electron withdrawing strength. This systematic design allowed fine-tuning of electronic properties and direct comparison of performance. The result? 8 unique molecules, each a distinct hypothesis ready for quantum testing. The stage was set to discover which digital creation held the most promise. With their molecular blueprints ready, the team turned to density functional theory, DFT, to predict properties. DFT focuses on electron density, allowing accurate calculations of molecular structure and energy. The first step, geometry optimization, letting molecules relax into their most stable shapes, crucial for accurate predictions. To study light interaction, they used time-dependent DFT, TDDFT, simulating how molecules absorb light. Choosing the right mathematical functional was key. The team compared several to ensure robust results. This careful approach ensured their predictions were reliable and scientifically sound. Their simulations laid the groundwork for understanding how these molecules would perform in real-world applications. The simulations revealed key properties, starting with polarizability, a measure of how easily a molecule's electrons are distorted by light. Pyrene-based molecules showed higher polarizability than phenylene-based ones, thanks to their larger, more mobile electron clouds. The main focus was the first hyperpolarizability, or beta, a direct measure of NLO performance. All 8 molecules exhibited enormous beta values, far surpassing standard materials. PY4, with the largest core and strongest acceptor, stood out with a record-breaking beta value. The trend was clear. Larger pi bridges and stronger acceptors boost NLO response. The team not only designed potent NLO molecules but also uncovered the principles behind their performance. Their digital blueprints now offer a roadmap for future material design. The next generation NLO material was born in silico. To understand their molecules' performance, the team analyzed electronic structure using advanced tools. Frontier molecular orbitals, FMOs, showed the HOMO on the donor and bridge, the LUMO on the acceptor, ideal for charge transfer. This spatial separation means that when light excites the molecule, charge shifts efficiently from donor to acceptor, driving strong NLO effects. Electron density difference, EDD, and transition dipole moment, TDM, analyses visualize this charge flow, confirming the DPA design's effectiveness. Natural bond orbital, NBO analysis, revealed pre-existing polarization, making the molecules highly responsive to light. Each technique added a piece to the puzzle, building a comprehensive picture of why these molecules excel. The result, a clear, intuitive understanding of their exceptional NLO performance. The team's analytical approach turned quantum data into actionable design insights. Beyond NLO applications, the team discovered these molecules could excel in organic solar cells. Strong light absorption and efficient charge separation, key for NLO, are also vital for converting sunlight to electricity. TDDFT simulations showed the Pyrene-based series absorbed visible and near UV light, ideal for solar energy. High light harvesting efficiency and impressive open-circuit voltages suggested strong photovoltaic potential. This dual-purpose discovery highlights the versatility of their molecular design. By pursuing better NLO materials, they also advanced solar technology. These molecules could impact both high-speed communications and renewable energy. The reliability of computational research depends on choosing the right theoretical tools. The team compared several DFT functionals, including long-range corrected types, to ensure accuracy. They found that while trends were consistent, absolute values varied. Long-range corrected functionals like CAMB3 LIP gave the most reliable results for these systems. This methodological rigor strengthens their findings and guides future researchers. Computational chemistry isn't a black box, it requires skill and critical judgment. By sharing their approach, the team has set a standard for robust, transparent research in material design. This research is a case study in the digital revolution transforming material science. Computational design flips the old paradigm. Now scientists define desired properties and design molecules to match, accelerating innovation. Virtual screening saves time, resources, and reduces environmental impact, making research more sustainable. This approach is becoming essential for green chemistry and efficient engineering. We're moving from observing nature to actively designing it, gaining unprecedented control over matter. The Phenalene and Pyrene study offers a glimpse into a future where materials are born in the mind and the computer, not just the lab. This is the new engine of progress across science and technology. This work is a vibrant thread in the tapestry of scientific progress, bridging quantum theory and real-world technology. The team's design of 8 novel molecules pushes the boundaries of nonlinear optics and opens doors for organic solar energy. PY4 stands out as a target for experimental synthesis, promising breakthroughs in both fields. Their approach validates computational design as a powerful tool for rapid, efficient discovery. By combining chemical intuition with digital power, they've illuminated a path for future scientists. This research is an invitation to explore the art of manipulating atoms and light, a key to a brighter, faster, and more sustainable future. The journey from concept to technology begins here with curiosity, collaboration, and the courage to innovate. Imagine a beam of light, once thought to be unchangeable, simply traveling in a straight line. For centuries we used light but couldn't alter its fundamental nature. But nonlinear optics changes everything. Here, light can transform itself, shifting color, path, and power when it meets special materials. Most materials respond to light in a predictable linear way. More light, more response, but always proportional. Nonlinear optical (NLO) materials break this rule. Hit them with intense light, and they react in surprising, amplified ways. They can merge two red photons into a single blue one, a kind of optical alchemy. These materials power technologies from fiber optic internet to precision medical lasers. The quest for better NLO materials is about engineering molecules to interact with light in extraordinary ways. It's a journey into the quantum world, where the arrangement and movement of electrons dictate optical properties. Scientists design molecules atom by atom, searching for the perfect structure to unlock new technology. This is molecular choreography, engineering at the smallest scale to create dramatic effects. The latest breakthroughs come from computational design, where researchers like Dr. Tazeem Fatima and her team build better materials from the ground up. By understanding and manipulating electron behavior, they're opening doors to the next generation of optical technology. Nonlinear optics isn't just about bending light, it's about reshaping the future. Let's explore how these molecular marvels are designed and what makes them so powerful. Building a molecule for nonlinear optics starts with a blueprint, not just random mixing. Dr. Fatima's team focused on phenylene and pyrene, stable, electron-rich molecular cores. These cores act as foundations, with mobile electron clouds that interact strongly with light. The real innovation comes from adding donor and acceptor groups, chemical attachments that push and pull electrons across the molecule. This creates a DPA framework, a molecular push-pull system that channels electrons when light hits. The result, a powerful, directed charge movement, essential for strong optical effects. Instead of trial and error, the team used computational chemistry, specifically density functional theory, DFT. DFT lets scientists simulate molecules, predict their properties, and optimize designs before synthesis. They tested dozens of donor-acceptor combinations, tweaking structures for maximum effect. This approach accelerates discovery, saving time and resources, while exploring vast chemical possibilities. Each simulation brought them closer to molecules with exceptional optical responses. The process is a blend of theory and creativity, designing, testing, and refining until the ideal molecule emerges. Modern science thrives on this synergy between computation and chemistry. From concept to candidate molecule, the journey is faster and more precise than ever. This is how the future of light is engineered, one molecule at a time. From this computational search, two standout molecules emerged, Phe4 and Pyrene. Phe4, built on a phenylene core, features a strong electron donor and a powerful acceptor, creating a dramatic internal charge shift. Pyrene uses a larger pyrene core, offering an even broader pathway for electron movement. The donor and acceptor groups were chosen for their ability to maximize electron flow. Their geometry ensures electrons travel the longest, most efficient route, like a thrilling water slide for charge. This design means a light wave can trigger a massive shift in the electron cloud, the essence of nonlinear optical response. Phe4 and Pyrene combine stability with extreme electronic polarization, ready to react powerfully to light. They're not random molecules, they're precision machines, crafted for a singular purpose. Their discovery is the result of intelligent, quantum-guided design. These molecules are poised to redefine what's possible in optical technology. Before diving into nonlinearity, let's understand linear polarizability, the molecule's basic ability to respond to light. When a light wave passes, it distorts the electron cloud, stretching the molecule. Linear polarizability, alpha, measures how easily this stretching occurs. High alpha means the molecule is squishy, easily distorted by light. Dr. Fatima's phenylene and pyrene compounds were engineered for maximum squishiness. Their aromatic rings and push-pull groups make them highly responsive. Computational models showed impressive alpha values, around 397 atomic units for phenylene, 492 for pyrene. The larger pyrene core allows even greater electron movement. High linear polarizability is crucial for optical materials. It means they can bend light effectively. This property underpins advanced lenses, waveguides, and more. By achieving such high alpha values, the team set the stage for even more dramatic nonlinear effects. These molecules are primed for action, ready to interact with light in powerful ways. Next, we'll see how this foundation leads to spectacular nonlinear behavior. When light intensity ramps up, think lasers, the response becomes nonlinear and dramatic. Third-order nonlinear polarizability, or gamma, measures how a molecule's response changes under strong fields. Most materials have negligible gamma, but Phe4 and Pyrene were engineered for massive nonlinear effects. Their donor-acceptor design exaggerates the electron cloud's movement, creating new light frequencies. Phe4's gamma, about 2.9 million atomic units. Pyrene, over 4.1 million, hundreds of times greater than standard molecules. These values mean unprecedented efficiency in manipulating light. High gamma is key for all optical switches, power limiters, and two-photon imaging. These molecules can control light with light, paving the way for ultra-fast computing and advanced medical tech. The leap in gamma isn't just incremental, it's transformative. Phe4 and Pyrene are more than curiosities. They're the building blocks for next-gen photonic devices. Their nonlinear power is the result of precise molecular engineering. The future of optics is being shaped by these quantum-designed molecules. What makes these molecules so responsive? It starts with their dipole moment, a built-in separation of charge. The donor group creates a positive region, the acceptor a negative one, forming a permanent dipole. When light hits, electrons leap from donor to acceptor, dramatically increasing the dipole moment. This charge transfer transition is key to strong nonlinear effects. The energy needed for this leap, the transition energy, is low in Phe4 and Pyrene, making them easy to excite. Low transition energy plus a big dipole change equals world-class NLO performance. Light triggers a quantum leap, shifting charge and amplifying the molecule's response. This interplay of structure, energy, and charge is the secret behind their huge gamma values. The team didn't just find high-performing molecules, they uncovered the quantum reasons for their success. Every detail, from dipole to energy gap, was engineered for maximum effect. This is the heart of nonlinear optics structure driving spectacular performance. Let's go deeper, into the quantum orbitals that govern these molecules. The HOMO, highest occupied orbitals, and LUMO, lowest unoccupied orbitals, are crucial for optical properties. A small HOMO-LUMO gap means electrons can be easily excited, exactly what Phe4 and Pyrene have. Their DPA design raises the HOMO and lowers the LUMO, squeezing the gap. But it's not just energy, the location matters. In these molecules, the HOMO sits on the donor, the LUMO on the acceptor. When excited, an electron physically moves across the molecule, a perfect charge transfer. This spatial separation explains the huge dipole change and nonlinear response. The design ensures electrons travel efficiently, maximizing optical effects. It's a symphony of quantum mechanics, orchestrated for performance. Every aspect, from energy gap to orbital location, was tuned for light-induced charge transfer. This is the molecular engine behind their extraordinary optical power. Discovering Phe4 and Pyrene isn't just a scientific win. It's a leap toward futuristic technology. Their nonlinear properties unlock new possibilities in optoelectronics and photonics. All optical switches could replace electronic ones, eliminating speed bottlenecks in computing and communications. These materials can enable light-controlled light, revolutionizing data processing. They're ideal for optical power limiting, protecting sensors from laser damage in defense, aerospace, and industry. Their charge transfer abilities also make them promising for next-gen solar cells and high-density data storage. Two-photon absorption could advance medical imaging and therapies. The journey from molecule to technology is long, but the path is now clear. These discoveries illuminate the future of light-based devices. The age of quantum design materials is here. Behind every breakthrough are visionary explorers, like Dr. Tazeem Fatima and her team. Their work is a beacon, showing how to design advanced optical materials from first principles. By combining computational power with quantum insight, they've created a blueprint for future discoveries. This research marks a shift from finding materials to engineering them with precision. Predicting properties before synthesis accelerates innovation and inspires bold new designs. Their results align theory with chemistry, giving confidence that these molecules will perform as predicted. The study demystifies nonlinear optics, offering a clear roadmap for others to follow. It will spark new research and push the boundaries of what's possible. Dr. Fatima's team has added a brilliant chapter to the story of molecular science. Their achievement reminds us, the quest for knowledge is the greatest adventure of all. In materials science, the race for better solar energy solutions is relentless. Scientists are searching for new molecules to capture sunlight and convert it into electricity more efficiently. A recent study in the Journal of Molecular Liquids led by Mohammed Khalid and colleagues dives into computational chemistry to tackle this challenge. Using advanced computer simulations, the team designed and tested new organic molecules long before any lab work began. This digital-first approach saves time, resources, and sparks creativity. The focus two types of molecules, phenylene and pyrene derivatives, known for their unique interactions with light. By designing 8 new compounds, the researchers explored how small structural tweaks can dramatically change a molecule's properties. This is modern science, using theory and computation to guide real-world innovation. The sun delivers more energy to Earth in an hour than we use in a year, but capturing it efficiently remains a challenge. Khalid's work is a foundational step toward next-generation solar cells, potentially more efficient and affordable than today's silicon panels. Instead of trial and error, scientists now build molecules atom by atom on a computer, predicting their behavior and selecting the best candidates for synthesis. This study is a testament to the power of computational design, offering a blueprint for the future of solar power. It's a story of innovation and the pursuit of a sustainable future. To grasp the impact of this research, we need to understand nonlinear optics, or NLO. Normally, light passing through materials like glass behaves predictably. This is linear optics. But with intense light and special materials, the response becomes nonlinear. The material can actually change the light's color or frequency. NLO materials are crucial for technologies like fiber optic communications, enabling high-speed data transfer by manipulating light itself. They're also vital in laser technology, medical devices, and even quantum computing. The search for better NLO materials is ongoing. We need strong, stable, and easily integrated compounds. That's where the new phenylene and pyrene derivatives come in. The researchers designed these molecules not just for solar cells, but for their NLO potential. By tweaking their structure, they aimed for an exceptionally strong nonlinear response. The key how electrons are arranged and how easily they move when hit by light. The better a molecule is at this, the more powerful its role in next-gen photonic devices. These advances could make our digital world faster and more efficient. The molecules in this study are at the forefront of that revolution. The core of this research is the smart design of 2 molecular families, phenylene and pyrene. These flat ring-based structures are rich in mobile electrons, ideal for interacting with light. But the magic happens when these cores are modified with other chemical groups. The team built 8 new compounds, 4 based on phenylene, Phe1 to Phe4, and 4 on pyrene, Pyrene to Pyrene. Each molecule features a donor group, a p-bridge, and an acceptor group, a classic DPA setup to boost light absorption and NLO properties. The p-bridge, connecting donor and acceptor, was systematically varied to test its effect on electron flow. For some, a simple thiophene ring was used, others had more complex electron-rich linkers. This allowed the team to see how bridge length and electronics impact performance. All of this was done using quantum mechanical calculations, specifically density functional theory, DFT. DFT predicts molecular shape, light absorption, and electron response with high accuracy. The result? A rapid, detailed screening of 8 complex molecules, all without stepping into a lab. This approach accelerates discovery, giving experimentalists a clear roadmap. It's a powerful example of how theory can drive real-world innovation. The groundwork for new materials starts here, in silico. The goal was clear: boost the nonlinear optical NLO response of these molecules. The key metric first: hyperpolarizability, or beta naught. Higher values mean stronger NLO effects. The team calculated this for all 8 compounds and saw a striking trend. As the p-bridge became more complex and electron-rich, the NLO response soared. In the phenylene series, Phe1 started at 10,642 atomic units, but Phe4 jumped to 54,642. The pyrene series was even more dramatic. Pyr1 at 13,383, but Pyrene4 skyrocketed to 123,019 atomic units. Pyrene4's structure, strong donor, strong acceptor, and the best p-bridge created a molecule tuned for massive charge transfer. This efficient charge movement is what gives Pyrene4 its standout NLO performance. The results show that rational design targeting specific properties works. By tweaking the p-bridge, scientists can fine-tune molecular behavior with precision. Pyrene4 isn't just good, it's a potential game-changer for advanced optical technologies. Computational chemistry is now guiding the way to next-gen materials. The proof-targeted tweaks can yield extraordinary results. To understand why some molecules excelled, the team used advanced computational tools to visualize electron movement. The transition dipole moment, TDM, measures how likely an electron is to jump to a higher energy level when hit by light, and in which direction. Ideal DPA molecules show a strong, clear flow of charge from donor to acceptor. Density of states, DOS analysis maps out which parts of the molecule contribute to its energy levels. In top performers like Pier 4, DOS showed strong overlap between donor, bridge, and acceptor, an electronic highway for charge. Electron density difference, EDD maps revealed dramatic charge shifts. Electrons move from donor across the bridge to the acceptor. For Pier 4 and Phe 4, this charge separation was clear and efficient. These analyses don't just say a molecule is good, they show why. They reveal the electronic processes behind strong NLO and solar cell performance. This deep insight lets scientists connect desired properties to electron behavior. Computational chemistry turns invisible electron dances into actionable design rules. The result? Smarter, faster development of high-performance molecules. The future of material science is built on this level of understanding. Beyond NLO, these molecules were tested for solar energy, specifically dye-sensitized solar cells, DSSCs. DSSCs use a dye-coated layer to capture sunlight and generate electricity, mimicking photosynthesis. The dye's properties are crucial. It must absorb a broad range of light, transfer electrons efficiently, and quickly regenerate. The team calculated each molecule's light absorption spectrum and key energy levels, HOMO and LUMO. The LUMO must be higher than the titanium dioxide conduction band for efficient electron injection. The HOMO must be lower than the electrolyte's energy for fast regeneration. The best performers, especially Phe 4 and Pier 4, showed strong, broad light absorption and ideal energy alignment. This means they can harness more sunlight and efficiently generate current. Their calculated properties make them prime candidates for real-world DSSC devices. Computational screening weeds out weak candidates before any synthesis. The result: faster, smarter development of solar cell materials. These molecules could help make solar energy more accessible and efficient. The future of solar technology starts with digital design. Two compounds stood out for solar cells, Pier 4 and Phe 4. Their strength lies in their ability to absorb light and efficiently transfer electrons. Calculations showed both absorb strongly in the visible spectrum, right where sunlight is most intense. Their light harvesting efficiency, LHE, is high, thanks to their DPA structure and strong charge transfer character. This means they capture photons and convert them to energy with impressive efficiency. The driving force for electron injection, energy difference between the dyes LUMO and titanium dioxide, is large, ensuring fast, effective current generation. Many dyes fail here, but Pier 4 and Phe 4 excel. Regeneration is also key. After donating an electron, the dye must quickly accept one from the electrolyte. Both compounds have HOMO levels perfectly positioned for this process. This completes the cycle, allowing continuous, efficient operation. In every metric, absorption, injection, regeneration, Pier 4 and Phe 4 are top tier. They're not just theoretical, they're ready for real-world testing. These molecules could redefine solar cell performance. To dig deeper, the team used natural bond orbital NBO analysis to examine electron interactions at the atomic level. NBO translates complex quantum data into a clear picture of bonding and charge transfer. The focus stabilization energy between donor and acceptor parts. Higher stabilization means stronger, more efficient charge transfer, exactly what DPA design aims for. Pier 4 and Phe 4 showed the highest stabilization energies, matching their standout NLO and solar properties. The analysis revealed strong interactions between donor lone pairs and acceptor anti-bonding orbitals, bridged by the P system. This creates a direct, efficient pathway for electrons to move. The electrons aren't just shifting, they're following a well-defined, energetically favorable route. This bond-level insight confirms that high performance is no accident. It's engineered. NBO analysis gives chemists clear rules for designing even better molecules. It explains how specific atomic arrangements lead to desired electronic behavior. With this knowledge, scientists can build molecules with the precision of architects. The future of materials design is intentional, not accidental. This study by Khalid and his team is a glimpse into the future of materials science. By designing and analyzing phenylene and pyrene derivatives, they've mapped a path to next-gen materials for optics and solar energy. Their theory-led approach identifies top candidates before any lab work, saving time and resources. Two compounds, Pier 4 and Phe 4, emerged as champions. Pier 4 for nonlinear optics, both for solar cells, Their exceptional properties are the result of targeted computational design. Tools like DFT, TDDFT, TDM, DOS, and NBO provide a complete picture from atoms to function. This transforms material science from trial and error to true molecular engineering. Researchers can now build function into molecules, atom by atom. The implications are huge: faster innovation for sustainable energy and advanced technology. This isn't just an academic exercise, it's a blueprint for real-world solutions. From computer screen to device, the path is clear. Computational chemistry is shaping a more sustainable, high-tech future. The next breakthrough in solar and photonic technology could start with a digital molecule. Welcome to the For Science Salah Lotfy channel. Today I'm taking you on a journey into the molecular world that's shaping the future of nonlinear optical materials. We're talking electron transitions, charge transfer, and the fascinating way molecules interact with light and solvents. Our focus? A groundbreaking study on phenylene and pyrene derivatives, specifically compounds Phe1 to Phe4 and Pyrene to Pyrene. Using advanced computational chemistry, researchers have unlocked secrets at the atomic level that could change how we design materials for next-gen technologies. First up, natural bond orbital, or NBO analysis. Imagine electrons as dancers on a stage, moving between energy levels. Here's what the researchers found. There are several main types of transitions: sigma to sigma star, pi to pi star, lone pair to pi star, and lone pair to sigma star. But the showstoppers are the p to pi star transitions, dominating across all molecules analyzed. Take Phe3, for example. It delivered a pi to pi star transition with an impressive stabilization energy of 24.14 kilocalories per mole. That means serious electron delocalization, a key ingredient for top-notch optical performance. Even more striking, lone pair to pi star transitions went as high as 72.22 kilocalories per mole, making these molecules highly reactive. Now let's talk pyrene derivatives. In Pyrene, the pi to pi star transition hit 23.49 kilocalories per mole. Pyrene wasn't far behind, reaching 23.85. And a lone pair to pi star transition in Pyrene clocked in at 37.73 kilocalories per mole. These numbers reveal strong donor-acceptor interactions, the kind that power nonlinear optical effects. Next, I'm looking at ionization potential and electron affinity, two metrics that define chemical reactivity. Pyrene had the lowest ionization potential at 4.29 electron volts, making it highly reactive and ready to share electrons. Meanwhile, Phe4 stood out with the highest electron affinity at 3.60 electron volts, prime for charge transport applications. These values, based on precise HOMO-LUMO energy differences, make these compounds very attractive for advanced optical and electronic devices. But what happens when you introduce solvents? Using the polarizable continuum model, the study looked at chloroform and methanol as environments. The results? Eye-opening. Pyrene's third-order nonlinear optical polarizability, gamma, jumped from 102.8 to 366.2 times 10 to the minus 36 electrostatic units just by moving from gas phase to methanol. Even more dramatic, Phe3's gamma soared to 5,726.5 in methanol. Clearly, solvent polarity can supercharge a molecule's optical response. To visualize charge transfer, researchers use natural transition orbitals, or NTOs. This method, even more accurate than the traditional HOMO-LUMO approach, showed electron transport contributions as high as 97%. That means electrons move efficiently from donor to acceptor, ideal for light harvesting and electro-optic uses. All 8 molecules had clear donor-pi-acceptor architectures, confirmed by Mulliken charge analysis. So what's the big takeaway? This deep molecular research opens new doors for designing dyes, improving solar cells, and advancing optoelectronic technology. Thanks to the collaborative efforts led by Dr. Tazeem Fatima, Dr. Shamsa Bibi, Dr. Shabir Muhammad, Dr. Shaukat Ali, and Dr. Muhammad Yassin, supported by King Khalid University, we're a step closer to smarter, more efficient materials. If you enjoyed this deep dive, subscribe to For Science Salah Lotfy channel, leave a like, and share your thoughts in the comments. Stay curious. And until next time, keep exploring the science of tomorrow. Welcome back to For Science Salah Lotfy channel. At the end of this episode, I'm spotlighting a fascinating study in the field of computational chemistry and nonlinear optics. This work is a true example of how quantum chemical design and theoretical modeling can lead to practical applications in advanced optical and optoelectronic materials. The research, titled systematic computational designing of efficient phenylene and pyrene-based derivatives to tune the optical and nonlinear optical response, is a collaborative effort involving brilliant minds from Pakistan and Saudi Arabia. Let me proudly name the contributors. Dr. Tazeem Fatima, PhD researcher, Department of Chemistry, University of Agriculture, Faisalabad, Pakistan. Associate Professor Dr. Shamsa Bibi, Department of Chemistry, University of Agriculture, Faisalabad, Pakistan. Associate Professor Dr. Shabir Mohammed, Department of Chemistry, College of Science, King Khalid University, Abha, Saudi Arabia. Associate Professor Dr. Shaukat Ali, Department of Chemistry, University of Agriculture, Faisalabad, Pakistan. Associate Professor Dr. Muhammad Yassin, Department of Physics, University of Agriculture, Faisalabad, Pakistan. This publication was released online on May 20, 2025, under the prestigious Springer Nature platform. This outstanding research explores advanced organic molecules, phenylene and pyrene derivatives, and investigates their linear and third-order nonlinear polarizabilities using state-of-the-art density functional theory techniques. Their work sheds new light on optical tuning, charge transport, and electronic structure design for future photonic and photovoltaic technologies. Such a study is not only scientifically rich, but also opens economic and technological doors for materials development. As we conclude this episode, I am Professor Dr. Salah Lotfy, professor at the Egyptian Atomic Energy Authority. And it is with great pleasure that I extend my heartfelt thanks to the research team for their exceptional work and scientific contribution. On behalf of myself and the entire team here at For Science Salah Lotfy channel, I sincerely thank all the researchers involved in this study for their dedication and valuable insight. And to our wonderful viewers, thank you for your continuous support. I invite you to share your thoughts, questions, or feedback about this research in the comments section below the video. Let's keep the scientific conversation alive.